So I believe we have over 20 students in this class, but so currently we have only 12. Okay, so I will start the class. So welcome everyone. This is Advanced Computer Architecture course. So this is the computer architecture course for graduate students. So this is the first class of this semester. So I will briefly introduce about this course. Also, I will cover some brief introduction to computer architecture. Okay. So what is the goal of this course? So actually, I believe most of you took the computer architecture course for undergraduate students. So actually, I copied the object of this course from the syllabus of the undergraduate course. So what is that? So exploring the, actually in the undergraduate course, I mentioned the exploring the computer system architecture at an abstract level. But this course is the advanced course for graduate students. So I insert the word advanced. So this is the advanced computer architecture course. Okay. Okay, what will be covered in this course? So as you can see in the undergraduate course, that is the concept of computer architecture. But in this course, we will learn about the advanced concept of computer architecture. So it's a more advanced course. So what have we covered? So performance metrics. So we will learn how can we measure the performance of computer systems. So that is very important, because what is the goal of this computer architecture research? So usually the goal of the most of engineering research area is to increase the performance of a certain system. And then that's also true for the computer architecture research. So actually the main research goal of the computer architecture research is to increase the performance of a computer system. So firstly, we will learn how to measure the performance of computer systems. Okay, and then we briefly covered what we learned in the undergraduate course. So we will review the pipeline process architecture. So that will be very simple. So actually, I believe the most of you learned the 5-stage pipeline, the processor in the undergraduate course. And then, so I will also cover some concept and the knowledge on this 5-stage pipeline processor. And then also we will learn about some more enhanced pipeline processor, such as the super pipeline processor. Okay, and then so in this course we will also learn this out of the process architecture. So this is very different from the simple 5-stage pipeline processor. So actually, the simple 5-stage pipeline processor is the very somewhat old knowledge. So it's old-fashioned actually. So actually, the modern high-performance processors employ out-of-the processor architecture. So this is a very important topic in this course. So we will learn about the architecture of out-of-order process architecture. Also, another important topic in this course is speculation. So what is speculation? Actually, the meaning of speculation in Korean is very weird. 한국어로는 투기라고 합니다. 투기. So in Korean, it means 투기, but it's weird. It's a weird meaning. Actually, the speculation means the prediction. So it's very important technique to improve the performance of computer systems. Actually, we frequently use this prediction technique in our real world. So we will learn about the speculation techniques in this course. And then parallelism. So in Korean, parallelism means 병렬화. So actually, I believe everyone knows about the word parallel. So it's very hard to pronunciate. So parallelism are also very widely used technique in the computer processor architecture. So I believe, so we frequently mention the number of cores in your laptop computers or desktop computers. So what does that mean? Number of cores. That means your CPU has multiple cores. So that means multiple tasks. So multiple threads can be executed concurrently. So why do we like multi-core processors? Because with the multi-core processors, we can execute many applications concurrently at the same time. Then that means so we can increase the performance of computer systems. So that's also very important topic in this course. So we will learn about the parallelism. And then CMP, chip multiprocessor. So I mentioned multi-core. So actually the multi-core means chip multiprocessor. So we will learn about the chip multiprocessor architecture. So actually in the in the next topic, so that means the introduction to computer architecture. So I will mention the chip multiprocessor architecture. And then memory systems. Memory system is also very critical for the performance of computer systems because every data exists in memories. Okay, and then what is the main purpose of your processor? So simply, processors read data from memory because the data is stored in memory systems, and this data is moved to the processing engines. So it's like ALU or some processing engines such as GPU cores like CUDA cores in NVIDIA GPU. So actually data should be transferred to these processing engines or near processing engines. So the performance of the memory systems actually determine the performance of entire computer systems. So that's why memory system is also very important topic in this course. So, but we will handle the advanced topics, not the undergraduate topics. So I expect, so you already know about some basic memory hierarchy, and then some basic pipeline process architecture. You learned in this undergraduate course. So I will cover some advanced topics in this course. Okay. Domain specific architecture. I missed this line. And then recently, recently, the many researchers have interest in domain-specific architectures. So what does that mean? So actually, so what's the processor? What is the CPU? So what does the CPU or CPU do? So CPUs can execute instructions, and then actually the CPUs can run applications. What kind of applications? It general purpose applications. Okay, so why do we like CPUs? Why do we like computer systems? because with our computer systems, actually these computer systems can run any kinds of applications. That's the main purpose of computer systems. So we call it programmability. Okay. But in order to support the general purpose execution or general purpose applications, the computer processor, that means the hardware of the computer system, need to support any aspect of applications. So in order to support the general purpose execution, then that means the processor needs to support any corner cases required by applications. And then what's the problem? The issue is that in order to support any corner cases, the computer processor's performances can be decreased. Also, another issue is the cost. The computer processors may consume much power in order to support the general purpose applications. Also, the performance is not reached to the maximum performance. Okay, the maximum expected performance. So, currently many researchers have interest in domain-specific architectures, such as what is the kind of domain-specific architecture? It's similar to GPU, is a graphics processing unit. So graphics processing units are designed for supporting graphics application. So it's different from CPU. So with the CPUs can run any applications, but GPUs are designed for executing graphics applications only. So it is specified for a certain domain of applications. So, but recently, actually the computer science field or computer engineering field changes very rapidly. So that means, so recently we rely on cloud infrastructure was data centers. Like it's like a very high performance server infrastructures. So that means the most of applications, even games, or think like a YouTube. So YouTube, the video is stored in the YouTube servers, and then we download the video, then or some videos are pre-processed, and then it is delivered to our clients, like a desktop or your smartphones. So many applications run on high performance server infrastructures, and then server infrastructures just run some specific domain of applications. Let's think like YouTube. So which application is required? So like graphic processing, or some encoding or decoding applications, and then also some data management applications. So specific applications are just required for some server systems, and then in order to support this, in order to increase the performance of this specific domain of applications, we focus on the domain-specific architectures. Okay, so this is the my plan to that. So I will cover these topics in this course. Okay, textbook. So I will use this textbook. It's the Parallel Computer Organization and Design, written by Michel Dubois, Aurélien Navarro, and Paul Strandstrom. So, I believe you can purchase this book from any internet bookstores. Also, during the classes, so I will provide the lecture slides for every class, and then sometimes I will list some suggested research papers, which will be very useful for understanding the some research areas, research topics in computer architecture. Also, I plan to introduce the architectural simulators for term project for this course. Okay. Then, so these are authors of this book. And then so additional material. So this is the very popular textbook in computer architecture research, computer architecture area. So it's the computer architecture quantitative approach. So actually this book is written by John Hennessy and David Patterson. So those authors are very popular. It's actually legendary. Those authors are legendary. It's a legendary researchers in computer architecture field. So you can read this book because this book is also very popular book, and then it will be very useful, beneficial. Okay, and then prerequisite, so strongly recommended. So as I mentioned, I expect most of you, so everyone took a computer architecture course for undergraduate students. So actually in Korea University, this course is the COSE 222. So actually, this is the in the undergraduate computer architecture course, the basic concept, the basic knowledges are covered by this undergraduate computer architecture course. So, and then I expect so every student knows the basic concept covered by undergraduate computer architecture course. Okay, and then also basic knowledge on programming languages. So this is the architecture course that is tightly related to the hardware system of computers. Okay, and there were some systems. So I mentioned computer systems. So in computer systems research area, so actually most of researchers use C, not Python. So Python is very easy to learn, and then it's very easy to use. But so usually, so the system programming is with the system formulas or system programs are written in C. So we sometimes I will mention some C codes in this course. Okay, and then basic knowledge on Linux commands. So I plan to use architectural simulators in this course. And then most of architectural simulators run on Linux operating systems. So you need to know some basic commands of the Linux operating systems. And then about me, so my name is 구건재. So this is my office. So my office is in 우정정보관, and then my office number is 43. And then if you have any questions or issues, then you can stop by my office but after making an appointment. Okay. Also, if you have any questions or issues, then you can email me with this email address, and then this is my web page, and then some lab page. You can find my address of my lab page. And then my research area is computer architecture generally. And then I focus on the process architecture, such as GPU process architecture, and then memory storage systems, accelerators, and then secure process architecture. Okay, like other courses, I will use the Blackboard for course management tool, but actually the Blackboard is not easy to use. Okay, so I will post some announcements and then assignments or thesis. I don't know. Oh yeah. So actually, I will use Blackboard for posting announcements. Okay, and then actually I will use this Piazza. So Piazza is the class management tool, and then I will post the some lecture slides and then course materials on Piazza. So please register to Piazza. Okay. So this is the address of the Piazza. So, and then if you go to the Piazza with this internal address, then you need to register to the course, this course. Okay. And then also you need the access code, and the access code is the Lake. So this is the most recent brand name of the Intel process architecture. So then please join as a student, okay, not TA or instructors. So, and then as I said, I will post the slides, videos, and then some materials on Piazza, okay? And then anyone can post questions, and then also anyone can post answers for the questions. So like this is the some research tab of the Piazza for undergraduate computer architecture course. So as you can see, I posted some lecture slides, lecture videos like this. So I will not post any slides or videos or any material on Blackboard. So it's not convenient. That's the reason. So I will post some course materials on Piazza. So this is the grading policy. So we will have a midterm, only one exam for this course. So and then so I will assign some homework for this course, and then I plan to offer some term project for the students. Okay, and then so exam. So just to read the some instruction. Yeah. So problem is that the COVID-19 pandemic is still severe. So that's the problem. So I believe the strength of the COVID-19 virus is rather weak, but the number of infected people is increasing very rapidly recently. So I think this situation is not good, but I hope we can pass this some difficult time. So actually, the department decided to offer online classes only for the first 2 weeks. I don't know. So I don't know. We can provide some in-person classes after two weeks. So I don't know because I cannot expect any future. So actually I provide the online classes only for the first 2 weeks. So this week and then next week. So this current plan. Yeah, problem is that the number of infected people is increasing very rapidly. So it's very important. I need to manage the number of infected students in this course. So I believe you already read some instructions from university, like regarding the COVID-19 situation. So we need to check the number of infected students in the classes in our class. So email me immediately if you are tested positive. 양성 나오면은 이메일 알려주세요. So let me know immediately if we are tested positive. What's this? It's just plan. So then online classes, I believe. So you already know. So actively participate in every class. That's very important. So and then also please turn on your video camera, because even though I provide the online classes, but I believe interaction is important in the class environment. So usually in Korean, so only instructor talks, and students just listen to instructors. Yeah, I understand because I'm also Korean. Yeah, but interaction is important. So please actively participate in every class. Also, so actually you need to register the every Zoom, right? Is it you need to register for every Zoom occurrence, right? So I will use, so you need to put your student ID for registration. So I will use this student ID or also your name for checking your attendance in this course, okay? This is the tentative schedule. So we have 16 weeks. And then just to remember the midterm day here, this is actually we have only one exam for this course. So we will take the midterm exam on the 13th week. Okay. So and then I plan we will take the this midterm exam during the regular class time. Okay. That's it. Any questions? Okay. So I move on to the topic.
교수님
네.
질문 있긴 합니다. 그
네.
과제랑 프로젝트가 아까 있었는데 좀 어떤
네.
식으로 뭐 좀 나오는지 궁금합니다.
뭐 과제는 아무래도 이게 그 대학원 수업이니까는 어떤 시뮬레이터를 사용한다든지 어떤 아니면은 그 벤치마크를 돌리면서 뭐 좀 퍼포먼스를 체크한다든지 이런 식의 약간 뭐 문제풀이가 아니라 그냥 뭔가 해보는, 그러니까 실습을 해보는 그런 과제들이 나올 것 같고요. 프로젝트는 어쨌든 시뮬레이터를 사용을 해가지고 아주 간단한 간단한 이제 뭔가 이제 리퀘어먼트를 이제 줘서 그 간단한 프로젝트를 하는 정도로 이제 생각을 하고 있습니다.
그럼 프로젝트도 뭔가 이제 뭐 프로포저를 쓰는 건 아니고 실습 위주로 진행이 된다는 말씀이시죠?
네, 아무래도 뭐 한 학기 동안 뭐 이렇게 뭐 새로운 걸 하기는 좀 어려울 것 같고요. 그래서 뭐 리퀘어먼트를 주든지 아니면은 뭐 지금 생각으로는 좀 많은 학생들 생각보다 좀 많은 학생들이 이 과목을 듣기도 하고 또 아무래도 연구 분야는 다 다르기 때문에 뭐 가장 좋은 거는 과목 프로젝트를 하면서 자기 연구랑 이제 연관돼 있는 그런 프로젝트를 자기가 좀 알아서 하면은 좀 제일 좋긴 한데 좀 그거가 어려울 것 같기도 해서 그거는 좀 어느 정도 이제 좀 약간 리퀘어먼트 나는 조금 큰 숙제 정도 이렇게 생각을 하고 있어요.
예, 알겠습니다.
음, 네, 질문 없으면은 그냥 오늘은 뭐 빨리 끝나긴 할 텐데 그래도 그 실라부스만 얘기를 하고 끝내기는 좀 그런 것 같아서 뭐 간단하게 이제 그 컴퓨터 아키텍처 리서치에 대해서 좀 소개를 하도록 하겠습니다. So I briefly introduce about some overall computer architecture research topics. So So this is the outline of this today's class. So I will briefly introduce about some computer architecture research, and then also I will briefly show how the computer systems are organized, and then I will introduce the technology factors and the trends. So as you know, every processor is a product of the semiconductor technology. So that means this semiconductor technology is very important for the performance of processors. Okay? So we frequently call the CPU is a chip. Actually it's a semiconductor chip or VLSI chip. So actually the performance and then some cost of this computer processor chip is tightly related to some technology in semiconductor. Okay, so I will also introduce some brief technology factors and trends in the semiconductor industry. Okay. What is computer architecture? Oh, sometimes, sometimes I am asked about my research area of computer architecture, and so I believe sometimes it is called computer 구조 in Korean. So what is 구조? So what do I do actually for this computer architecture research? So we already know about the hardware and software of the computer system. So we know the hardware is the real things, or it's a real machine that runs computer software. And the software is just the software, it's application. Actually, the software is the group of instructions. So that's it. It's just the software. And what is computer architecture? So actually, the old definition of the computer architecture is just an instruction set architecture. So I believe everyone knows about the instruction set architecture because the prerequisite is the undergraduate course. So if we just if someone says so I'm working on the computer architecture research in the previous decade. Some several decades ago, then it just means that we are working on developing some better instruction set architectures. Or if we just mention the computer architecture, then it is tightly related to just instruction set architecture. But today's definition is much broader because computer architecture covers the wide range of the computer systems. So definitely, computer architecture handles the hardware organization of computers. Okay? So if we just say about the computer architecture, then we just focus on the hardware of the computer systems, like the process architecture or memories or memory system architecture. So as you know, processors, memories, and then some peripherals such as the I/O systems are all hardware. So if we just say, so we are working on the computer architecture research, then it means just a hardware organization of computers. So some traditional meaning of the computer architecture research. And then we also focused on the how to build computers. So in the syllabus, I mentioned what is the good computer. So actually, I mentioned the performance metrics in the syllabus, and then actually everyone wants to have very high performance computer systems. So also, we don't want to consume much energy. So actually, the goal of the computer architecture research is actually the goal of every engineering research is to increase the performance of the system and reduce the cost of systems. So it's also very important in the computer architecture research because we focus on the hardware. We are working on how to build computers, so including instructions and architecture. So these are some very traditional concept of the computer architecture research. And then we also focus on the interfaces between hardware and software. So I will also explain about the layers in computer systems, and then also I will also explain about some areas of the computer architecture research. But usually computer architecture means handles the interfaces between hardware and software. So if you are interested in this research area, then you can find that some universities have computer architecture research in electrical engineering department, or some universities have the computer architecture faculty members in computer science department. So because the computer architecture is just covers the interfaces between hardware and software. So in the Department of Electrical Engineering, the computer architecture is the topmost layer. So in the Electrical Engineering Department, and in the Computer Science Department, the computer architecture area is the bottommost layer in the department. Okay, because it's interfaces. It's just handles the interfaces between hardware and software. So what is covered? So I just copied my syllabus in the computer architecture course for undergraduate students. So in the undergraduate course, we covered these topics. Okay, but as you can see, we learned about the performance metrics. We learned about the instruction set architecture. We learned pipelining, so processor architecture, and memory hierarchy, parallel process architecture. Oh, that's the traditional research area of computer architecture. But let's see the recent research topics in computer architecture. So I just list the title of the Micro 2021 conference. So I just list the session list in Micro. The Micro is the top tier computer architecture conference. So as you can see, so what are the session names? Non-volatile memory, energy efficiency, and low power. It's traditional also. And security and privacy, processing in or near memory, parallelism. Okay, it's very familiar. Accelerators, reliability, GPU, microarchitecture. Oh, this is the very traditional computer architecture research. And then superconducting and quantum. What's that? It's just physics. And then sparse processing, graph processing, virtual memory, and prefetching. Oh, this is memory systems. So, can you find any common topics in the computer architecture research of the undergraduate course? That means the traditional topics, and then the recent research topics in the top tier conference. So we can find only microarchitecture, virtual memory, and prefetching, and then energy efficiency and low power, and then parallelism. So recently, computer architecture research covers various aspects of computer systems. Also, as you know, the computer system research or computer technology changes very quickly. So that means the research topics, so popular research topics or research areas also changes very quickly. So if you just see the topics of the conference, then you can find, oh, very new topics. So security, oh, what's that? So I'm not a security person, but we are working on security also. So this security is based on some hardware security. And then how about the non-volatile memory? I'm not a EDA or some digital system design person, but we need to know about some characteristics of the non-volatile memory because the memory is also changing recently. And then accelerate, what does that mean? GPGP. So these are the new type of processors in computer systems, okay? Like domain-specific architectures. About the superconducting and then quantum. It's area of the physics. Oops. So computer architecture research covers various research topics related to computer systems. Okay, so this slide shows the layers in computer systems. So actually, this figure is I believe this figure is very popular because I copied this figure from the undergraduate digital logic design textbook. So as you can see, computer systems are composed of many different layers. So, and then it's not possible to understand every layer because recently the computer system is very complex system. So that means it's very hard. We cannot understand every aspect of the computer systems. So we just focus on such layer among many layers. And then also computer architecture just covers these two layers, like architecture and microarchitecture. So this is another figures of the computer system layers. So as you can see, this figure has I copied this figure from the textbook, like textbook, parallel computer organization. So the computer systems are composed of applications. It's the normal user applications and the compiler and libraries and operating system. So these are area of software. And then, as you know, so many computer engineering students or computer science students focus on application. It's the topmost layer of the computer system. But we are system guy. I believe the most of you are system guys. So we just focus on the lower layer of the computer system, like operating systems, instruction sets, or computer system organization architecture. So usually the traditional computer architecture covers these two layers, like instruction set architecture and computer architecture, computer organization, also process architecture. And then recently our area is expanding. So sometimes we focus on the operating systems. Also, as you can see, we focus on the security issues. So we focus on some very weird topics such as the quantum computers, like physics level. Okay. So what is the role of a computer architect? So it's a computer architecture research. Make a design trade-offs across the hardware and software interface. So it's very important because we are handling some interfaces between hardware and software. So as you can see this figure, this is the software layers and these are the hardware layers. So where is the computer architecture between software and hardware? So we are developing the better interfaces between software and hardware, then focus on the performance and cost. But recently we focus on many different aspects in computer systems. Okay, then what is a computer system? So this figure shows the organization of a very typical computer system, but this is the I mentioned a little bit old, but it's very old computer system. Architecture of the very old computer systems. So if you see that this news bridge, then it means it's very old system. So actually the history of the computer architecture is very long. So and then also the history of the computer architecture is it's similar. It's similar to the history of semiconductor technology. Because what's the first computer? The first computer was built using vacuum tube, and then after that, the very old computer systems was built using bipolar transistors, and then using CMOS transistors. So the process architecture or the computer systems are tightly related to the history of semiconductor technology. And then in a few decades ago, about 30 to 40 years ago, the semiconductor technology was not as good as the current technology level. So that means the CPU chip just includes the very small number of transistors. So the nose bridge is not included in the CPU chip. Also, as you can see, you can find the off-chip cache. So that means actually in the very old CPU does not have L2 cache. So the old CPU has just on-chip level 1 cache, but level 2 cache is what is outside of the CPU chip. So it's very weird. It looks very weird, but because this is the oldest computer system, so we cannot include some level 2 cache inside of the single CPU chip. So this CPU chip is connected to another nose bridge chip, and then nose bridge chip is connected to some GPUs and then main memory. Then there is another hierarchy here, so you can find the south bridge chip. So as you can see, we use many different components in a computer system. So a computer system includes CPU and main memory like DRAM. Also, some computer systems have GPUs, and then many I/O devices such as keyboards, storage, mice, networks are connected to our computer system. But that means various devices, very wide range of devices are connected to computer system. That means latency, performance, speed of these devices are very different. So usually graphics processors or main memory require wide data bandwidth, right? So those components require very high performance data movement. So these high performance devices are located near CPUs. How about the other I/O devices, very slow I/O devices, such as keyboard, mice, or network interfaces? So these devices are very slow. So we have another hierarchy, like South Bridge, and then these slow devices are connected via South Bridge chip. So this is the traditional organization, the organization of traditional computer systems, very old computer system actually. But if you see the diagram of the modern motherboard chipset, then we can find this modern PC architecture, so architecture of the modern computer systems. So as I mentioned, the most of modern CPUs include the nose bridge chipset. So that means the graphics processing units and DRAMs are directly connected to the CPU. And then this CPU is connected to motherboard chipset. So actually this chipset is the South Bridge chip in this old computer system. So as you can see, many peripherals are connected to this connected to CPUs via motherboard chipset. Okay, so we can use the PCI interface like this, like the PCI Express 3, and then SATA, and then USB. Also, this motherboard chipset is connected to some different functions of the computer system. Okay. So, and then as you can see, you can find that, oh, this is the motherboard chipset of motherboard chip of 8th generation Intel Core. How about the most recent Intel Core? So it's the most recent computer system architecture, and as you can see, oh, this is the CPU, and then oh, DRAM. It's very actually the organization is very similar to this figure, but you can find that some interfaces are changed. So for the 12th Intel CPU, 12th generation Intel CPU, we can use the DDR5. So why do you use DDR5? To support wider bandwidth, the higher bandwidth. So we can find this number. So compared to the, we cannot find any bandwidth information here for you, but we can calculate. But the modern computer systems support wider data bandwidth. So that means that faster memory or the memory that supports the wide bandwidth. It's very important. Also, the GPUs are directly connected to the CPU. Then as you can see, the PCI version is also increased. So we can find the bandwidth values here. So some storage devices such as the SSD also support the high bandwidth. Why? High bandwidth is required for modern computer systems. Okay, so this is some conceptual view of the general high-end parallel systems. So You can see, as you can see, this is the core. So it's a separated computer CPU chip. And then, I don't know, it's cache, sorry, it's cache. And then processor is here. So you know, the processor includes the on-chip cache, because if the data is found in these on-chip caches, then we can access this data very quickly. So on-chip cache is very critical for the performance of processors. Also, the main memory is connected to this processor via memory bus here. So this is the, it's very similar to the organization of personal computer. The personal computer, like Intel i7 or i5, i3, has the on-chip cache here, and then the main memory is dedicated. The main memory is directly connected to this processor. So this is the PC setting. And then another core and memory is connected via interconnection network. And then through this interconnection network, storage devices and then other IO devices are connected. This is the general organization of the high-end parallel systems. So many CPUs are equipped in the single motherboard. That means the high performance server systems, and then each processor chip is connected to its own main memory. Okay, and then these processors are connected via interconnection. It's a common interconnection bus. So this is the typical organization of the high-end, so high performance server systems. Okay, then what can you find here? This memory organization is called NUMA. So what does NUMA mean? So NUMA means non-uniform memory access. Okay, non-uniform memory access. So what does that mean? Actually, this processor can access data in the near memory here, so dedicated to main memory. Also, this processor can access the data in the connected to different processor, like here. So if this processor access the data in this memory number 2, then it can access the data very quickly because it's connected to this local interconnection. How about the data in this memory number 1? It is located in this processor. So in order to access this data in this memory, then it will take a very long time. So even though, but to the programmer, so this is the hardware setting, but to the programmer, it's a very simplified illusions provided to the programmers. So what is this illusion? To the programmers, there is very limited number of cores, and then this limited number of cores can access very large memory in the computer system. That's programmers' illusion. It's a fantasy actually, but it's not real. So we are working on the real world. So usually the programmers play in the fantasy world. So in the real hardware setting, the cores have its own dedicated memory, and then these dedicated memories are connected to different cores. So if the data is accessed from the different core, then it will take a very long time. So why did I mention long time? Because it's related to performance of a computer system. Okay. So it's programmer's illusion, but programmer's illusion is different from real configuration. So I just showed some topology introduced by Intel. So we just used this high performance server configuration in the server systems. So as you can see, so server systems can have multiple CPUs like this, and then memories are connected to these separated CPUs. But in the server systems, the CPUs can communicate each other, okay, like this. So this is NUMA system. So we frequently use this configuration for high performance server system. So, and then there are many research topics in this high performance and actually NUMA systems. Okay, because we just provide this illusion, but under this illusion, there is very difficult word. It's a dirty word. 네. 어쨌든 요거를 좀 이제 설명을 해준 이유는 우리가 쓰는 많은 그 하이 퍼포먼스 시스템이 많이 누마라는 누마 구조를 가지고 있고요. 그래서 누마 구조를 가지고 있고, 우리가 이제 소프트웨어하고는 다르게 하드웨어는 리얼 월드에서 이제 놀기 때문에 컴퓨터 아키텍처는, 그래서 실제 그 소프트웨어가 생각하지 못하는 뭔가 아까도 말했듯이 소프트웨어는 이런 판타지 월드에서 논다라고 했잖아요. 인피니트 넘버 오브 코어를 가지고 있는 very large unified 메모리를 가지고 있는 시스템이라고 가정한 채로 소프트웨어는 작성이 돼요. 실제로는 그렇지 않기 때문에 이 그 하드웨어의 컨피규레이션과 하드웨어의 어떤 아이디어에 따라서 퍼포먼스가 굉장히 이제 달라집니다. 그거를 좀 말을 한 거예요. And then in this NUMA setting, we have many research topics. 네, 리서치 토픽도 뭐 많이 생각할 수가 있습니다. 그래서, and then I mentioned the process performance history of the process architecture is tightly related to the history of semiconductor. That means the semiconductor technology. So if we just focused on the performance of a CPU, then firstly we just check the clock frequency. So if the clock frequency is high, that means these CPUs run very quickly, right? Then how can we implement this high clock frequencies, high clock rates? So if we use the very fast transistors, then we can implement the high frequencies in CPUs. So that's why the advanced semiconductor technology is required for high performance CPUs. But so this graph shows the highest clock rate of Intel processors from 1990 to 2008. So this is some trend of this highest clock rate. So as you can see, this is the just expectation. So clock rate increases exponentially based on this expectation. But around the early 2000, okay, as you can see, this is the real trend. The clock frequency is saturated. So what does that mean? So so recently we are using the very advanced technology node in semiconductor, such as the 5 nanometer one. So we are mentioning the 2 nanometer technology in the semiconductor lithography. Yeah, so technologies are advancing one by one, but clock frequency is saturated. So what does that mean? Why this clock frequency? Why is clock frequency saturated? It's the power issue. Because the semiconductor technology is advancing, we may manufacture the very fast CPUs. So that means that the CPUs so running with very high frequencies. But so P is CV/F square, so actually proportional. So this is the capacitance, this is the voltage, and this is frequency. The power consumption of processor is proportional to the square of frequency actually, but the supply voltage is also proportional to the frequency. So actually the power is proportional to cube of frequency, clock frequency. So what does that mean? So we may implement the very high frequency in our CPU processors, but this CPU will consume very much power. Then it is not desirable. So cost is also important. If our computer system consume the how can I so consume the power consumption of that air conditioner. So it's much higher than the air conditioner. Then no one will use our computer system. Okay, so because of the cost issue, like power consumption issue, the clock frequency is saturated. Okay. So usually we can say that this exponentially increased power clock frequency can be helped by the exponentially increasing clock frequency benefits from the advanced technology in semiconductor. But we can say that this curve is the exponential factor is just 1.19 by semiconductor technology. But as you can see, the computer processor was achieving 1.49 exponential factors in their clock frequencies. So this gap, so 1.49 is better than 1.19. So this gap is caused by deeper pipeline, so architectural effort, and then circuit design technique, but also the process improvement. Okay, so the architectural effort is also included in the development of this processor design. Okay. Okay. This graph shows the number of transistors here, and then the feature size of a single transistor here. So this graph and then this graph represent the number of transistors in a single CPU chip, and then this graph shows the channel width of a single transistor. So if the channel width of the single transistor is small, so that means that size of a single transistor is also small. So it's a channel width, but the chip is the 2-dimension. So if the channel width is reduced by 1/2, it's a half sized, then the area of a single transistor is reduced to 1/4, because the area is square of the square of length. Okay, so as the semiconductor technology advances, then the size of transistor is reduced, and then also definitely the number of transistors in a single chip increases. So as you can see, this is the log scale axis. So which means the number of transistors in a single chip increases exponentially. So that is Moore's law, right? But if the Moore's law continues, then that means so we can include much more transistors in a single chip. So if this trend of the Moore's law continues, so we are living in 2022, but it's just expectation because it's some old data. So we can reach the 100 billion transistors in 2021. So is it possible? So the technology node reduced by 30% every process, and then half to every 5 years. So that means we are looking at the 5 nanometer or 2 nanometer or 10 nanometer technology in the semiconductor lithography. But the Moore's law continues? No, actually not. So Moore's law is facing its end. So we need to develop some ideas to overcome the actually the Moore's law is ending. So but we need to develop the higher performance processors. So we need to develop some new ideas in the process architecture actually. So 100 billion. Can you find the 100 billion chips in a real chip? So typical number of transistors of the very large chip is about recently, I think it's about 10 billion, like NVIDIA GPUs. But we cannot reach the 100 billion transistors in a single chip, but it's not true actually. So what is this? It's the largest chip in the world. So it's actually it's Cerebras. I don't know. But it's the largest chip in the world, and then this chip is actually the wafer scale chip. So there are 1.2 trillion transistors in this single chip, as you can see. But the chip size is very large. Actually, this is very ridiculous because this chip will be very, 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 very expensive. What does that mean? So usually the chip size is, so we maintain the chip size because the chip area is related to the price of chip. So if the chip size is large, then many defects can be included in the some area of chips. But if a single defect is found in a chip, then we cannot use this chip. So this chip is called stone because the major component of chip is silicon dioxide. It's similar to sand. So sometimes if the chip has defect, then chip has, so we can, if you cannot use a chip, then it is called stone. So if the chip size is very large, then this chip may in fact include some defects here, and then some defects are found, and then if we cannot use this chip, then we cannot use this chip. So actually the chip size is small. this chip is, it's a very weird chip actually, and then this chip includes the 1.2 trillion transistors. But it's 이거는 사실 그런 비정상이라고 할까요? It's some abnormal trend. So normally the largest chip in the world is about the 10 billion, includes the 10 billion transistors. So we can facing the end of Moore's law. We are facing. And then memory systems. So I briefly covered about the semiconductor technology and then processor technology node. And then, so let's focus on the memory systems. How about the performance of the memory systems? So if you just focus on the clock frequency of the Intel CPUs, then you can find that, the clock frequency of the Intel CPU is about the 3 gigahertz. Or so recently it can reach 5 gigahertz. It's very fast. But how about the frequency of the main memory, like DRAM? It's about the 1 point blah 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 gigahertz, right? So main memory speed is still slower than the clock frequency of processors. So that means the memory speed is slower than the speed of the processor. But as I mentioned, every data exists in main memory. The processor fetch data from this memory, and then the processor can execute instructions only using this fetched data. So memory speed is very important. Okay, that's why we are using memory hierarchy. But memory speed is still slow. So this is called, so actually the performance of memory systems determine the performance of entire computer systems. So this is called memory wall. So memory wall means that the memory is slow, but the processor is fast. So the performance is determined by these slow memories. So this is memory wall. But as I mentioned, to the programmers illusion is that, it's the large number of processors. There are a large number of processors, and then there is large, fast memories in our computer systems. That's programmers' illusion. So ideal memory is big, large, and fast, and cheap. But we cannot use this type of memory, so we have memory hierarchy. So memory hierarchy relies on locality, data locality. So data locality is also very critical. So we have cache memories. So we have register files. So the processor has cache memories. A processor has register files. Okay. So memory is also very important research area in computer architecture. So We can compare the size, typical size, and then cost per data, and then access time of the different types of memories. So usually it's like tens of nanosecond. So L2 cache is so recently it's fast because this data is from 2012. So that's why. So slow memory is size is large, but it's very slow. So that's why we are using memory hierarchy. Yes. Then how about the memory wall? I mentioned the clock frequency of CPU is saturated. So, but the memory speed is slightly just increasing, continuously increasing, because memory was very slow compared to the processor. So we have some more rooms to increase the clock frequency of memory systems. So as the memory continues, the memory speed is increasing continuously, but the clock frequency is saturated. So the gap of a memory wall is reducing. So it's a good thing. But the memory is still slow. So that's why we focus on some memory research, or we are focusing on better memory, like so faster memory or large memory. So we are focusing on this memory research. But recently, the more important factor in memory system is bandwidth, right? So the processors includes many cores. Okay, the recent Xeon cores have tens of about the 20 to 30 cores. And then, but as you can see, these cores are connected to the RAM via memory controller. So inside of this Xeon CPU, many cores are connected via interconnection network, and then one node of the interconnection network is connected to the memory controller, and then the DRAM is managed by this single memory controller. So what does that mean? There are many cores and then single DRAM, and then so many cores require more data. So this DRAM need to support the higher bandwidth to multiple cores. That's why bandwidth is critical for the modern memory systems. So think like a GPU. So recently the GPU is equipping high bandwidth memory, HBM, even though the HBM is very expensive, and then also the chip count is very large, but the GPU memory needs to support very large, high bandwidth. Why? GPUs are learning hundreds to 1,000 threads concurrently. So that means these large number of threads require high bandwidth from memory. So recently, the high bandwidth is more important. Okay. Latency is also important because latency is directly related to the performance of memory systems, but bandwidth is also important. And then another issue is that the application, the recent modern applications handle very large data. So that's why we mentioned that this type of application is big data applications. So because the modern applications handle large size of data, this data exists in the memory. So the memory size should be very large, and then large data should be required for processing. So the memory needs to support the high bandwidth because the CPU, the processors need to access the large sized data. Okay. And disk is the slow storage device. So the density is also increased, and then so disk is a storage device, and conventionally we use hard disk drive, that's the mechanical drive, and then so actually the disk is very slow compared to the main memory, but our data exists in disk because disk is a non-volatile memory. So even that means that the user data is permanently, not permanently, it's called persistently. The persistently stored in the disk. But disk is very slow, but it's not directly connected to the performance of the computer system because the data is transferred to the main memory from the disk, then this performance of the DRAM was critical. Okay, but the disk technology was also advanced, so we can use the very fast disk. Also, we can use the high density storage devices. So, but recently we are using SSD. SSD is faster than the hard disk drive, and then SSD use the flash memory as the main storage media. Okay, so the trend can be different. And then another issue is that, as I mentioned, the very popular applications are big data applications. And then how about the user data? The user data exists in storage devices. So because very large sized data is required by application, the disk access is very frequent in the modern computer systems. That means the storage device performance also determines the performance of an entire computing system. That's why we also focus on the performance and then some research topics in storage devices. So traditionally, storage device was the research area of the operating systems, but recently, many computer architecture researchers focused on the storage devices because of big data. Okay. So networks. So network is just networks. So many computers can be connected via network systems, and then so actually, how about data center? Those computers in the data centers are connected to each other via network interfaces. So sometimes in the data centers, the performance of the network interface is very critical, right? What is data center? So I also explained about the illusion of the programmers, but another illusion of not programmer, another illusion of a user is that it's cloud computing. It's data center. The illusion of a user for this data center is that data center is one computer, and then users are using this very large one computer system. So to the users, their data can be located in a certain server systems where some networks attached to storages, but user does not know about that. user just access their data. So it looks like there's a CPU and then the storage. That is user's perspective for data center. But in the real world, in a data center, so there are a large number of servers, and then servers are connected to network attached storages or network. Also, servers are connected to each other via network interfaces. So what does that mean? The performance of data center, the quality of service in the data center can be determined by performance of networks. Okay. So computer architecture research also includes the data center infrastructure research. So some researchers focus on the network performance. Also, recently, some researchers focus on some smart networks, where the processing in networks, data center. Okay, so there are many research topics in the modern computer systems. Okay, but okay. So I briefly introduced some components in the computer systems, and then some trends, and then aspect of these components in the computer systems. So we have only 3 slides, but I think I can cover these slides in the next class. So I will stop here, and then I will cover the remaining slides in the next class. Any questions? 네, 첫 시간인데 좀 오래됐네. Okay, thank you for your attention, and then see you in the next class. Thank you, guys.